Okay, so here's something that's going to mess with your head a little. Right now you're watching this video, and you cannot, no matter what you do, watch it, unwatch it. You can't undrink that coffee you had this morning. You can't unsay that embarrassing thing you said in 3rd grade. Time moves forward, always forward, never back. But here's the thing that keeps physicists awake at night. The laws of physics don't actually require that, like mathematically. Time could go backwards. The equations don't care. If you filmed 2 billiard balls colliding and played the video in reverse, it would look completely normal. Nothing in the physics of that collision says, this is running backwards. So why does everything in real life feel so obviously, stubbornly one-directional? Why can't you unscramble an egg? Why does ice always melt into water and never the other way around on its own? Why does your room get messier over time and never spontaneously clean itself? The answer to all of this, and I mean all of it, comes down to one of the most wild, underappreciated ideas in all of science. And once you get it, you will never look at time the same way again. So let's start with something weird. Imagine you have a box, and inside that box you have just 2 air molecules, just 2. One on the left side, one on the right side. Now, if you open a little door in the middle and let them move freely, where will they end up? Well, they could both be on the left, or both on the right, or one on each side. There are basically 4 possible arrangements. And here's the thing, each one is equally likely. Okay, now scale that up. Instead of 2 molecules, you have 4. How many ways can you arrange 4 molecules in a box? A few more, 16 to be exact. But here's where it gets interesting. There's only one way to have all 4 molecules on the left side. Only one way to have all 4 on the right. But there are 6 different ways to have 2 on each side. So the spread out evenly arrangement is 6 times more likely than the all huddled on one side arrangement. Now imagine not 2 molecules, not 4 molecules, but like 26,000 billion molecules, which is roughly how many air molecules are actually in a room. The number of ways to arrange them so they're roughly spread out evenly. Astronomically, mind-bendingly, almost incomprehensibly larger than the number of ways to have them all piled in one corner. We're not talking 10 times more likely. We're talking numbers that would take longer to write out than the age of the universe. This idea, this counting of possible arrangements, it has a name. It's called entropy. And it's basically the universe's way of saying more ways to more likely to happen. That's it. That's the secret. The reason time goes forward is because the future has more possible arrangements than the past. Let me say that again because it's so good. The future is just statistically messier. And the universe is lazy. It doesn't pick where to go. It just falls into whatever arrangement is most probable. And the most probable arrangement is almost always the messier, more spread out one. Now here's the version that'll really blow your mind. Think about that egg again. A whole egg has a very specific, very particular arrangement of molecules. The yolk is here, the white is there, the shell is holding everything together. That's a Lebov entropy state. There are relatively few ways to arrange the molecules of an egg so that it looks like a proper egg, but a scrambled egg. There are countless, virtually infinite ways to arrange those same molecules into a scrambled mess. You could scramble it T-ice way or T-ati way, or 10 to the power of a gazillion other ways. So when you crack that egg and mix it up, you're not doing something against physics. You're doing something that physics overwhelmingly prefers. You're surfing a wave of probability, and that wave only goes one way, because going from scrambled to whole egg would require finding, out of those 10 to the gazillion scrambled arrangements, the only specific arrangement that makes a perfect egg again. The chances of that happening spontaneously, it's not 0. But it's so close to 0 that you'd have to wait longer than the universe has existed, and then wait that long again. And then a few more times just to be safe. It won't happen. Not in your lifetime, not in anyone's lifetime. So entropy is the arrow. Entropy is why time has a direction. But now, and this is where it gets genuinely quantum, level weird. We have to ask, why was entropy low in the first place? Because here's the thing, if the universe started in a HH entropy state, already messy, already spread out, there'd be no arrow, no direction. Time would feel like nothing, or everywhere at once. The fact that time has a direction, the fact that, you can remember your past, but not your future, the fact that causes come before effects, all of that only works if the universe started in an incredibly ordered, incredibly low entropy state. And it did. The Big Bang wasn't just a big explosion. It was a remarkably, suspiciously, almost unnervingly tidy explosion. Everything was packed into an unimaginably small, unimaginably ordered point. Maximum structure. Minimum chaos. And ever since then, the universe has been doing what high entropy loves to do. Spreading out. getting messier, running downhill, probability-wise. And WE are somewhere in the middle of that slide, which is why we experience time as moving in a direction. We're riding the entropy wave. We're in a universe that started neat and is slowly becoming a mess. And the direction we call forward is just toward the mess. Okay, but now we get into quantum territory, because you might be thinking, sure, okay, lots of molecules behave statistically, but what about at the tiny scale? What about individual particles? Does time have a direction for a single electron? And this is where physicists start pulling their hair out, because quantum mechanics is deeply, fundamentally weird about time. Here's one example. You've probably heard of the double-slit experiment. Quick version, you shoot particles, like electrons, at a barrier with two tiny slits, and instead of landing in two bands like you'd expect, they create an interference pattern, like waves. Because in quantum mechanics, before you observe a particle, it's not really in one place. It's in a superposition, a spread-out probability cloud of everywhere it could be. And that probability wave passes through BOT slits at once. It interferes with itself. And only when you observe it, only when you force it to be measured, does it collapse into one specific location. Now, here's the time puzzle. The wave function, the math that describes where the particle could be, it evolves perfectly symmetrically in time. You could run it forward or backward and the math works fine. There's no built-in arrow. But the moment you measure it, the moment it collapses from everywhere it could be to here, specifically here, that process is not reversible. You can't collapse a wave function. You can't unmeasure a particle. The measurement, the observation, the interaction with the larger world, that's irreversible. And some physicists think that this moment of interaction, this entanglement between a quantum particle and the world around it, is where the arrow of time really comes from. It's not just about messiness and statistics at the large scale. It's about information. When a particle interacts with something, information gets written into the universe. And information, once written, can't be unwritten. The universe keeps records. Terrible, permanent, indelible records. Every interaction, every collision, every measurement, all of it permanently etched into the state of things. And because information only flows in one direction, because causes write themselves into effects, not the other way around, time has a direction. There's a concept called quantum decoherence that gets at this really beautifully. So a quantum particle in superposition is kind of like a secret. It hasn't committed to being one thing yet. It's still all the possibilities at once. But the moment it bumps into another particle, the moment it interacts with the environment, it leaks. The secret gets out. The surrounding environment now has information about the particle. They're entangled. And once you're entangled with the environment, you can't just go back to being a pure, uncommitted secret. The information is out there, spread across billions of particles in the environment. You'd have to round up every single one of those particles, reverse all their states perfectly, and undo every interaction simultaneously. The probability of that is the same order of magnitude as your scrambled egg reassembling itself, effectively zero. So decoherence is the quantum version of entropy. It's the mechanism by which quantum weirdness fades away and things start behaving like the normal classical time respecting world we live in. And it happens because information leaks, and information leakage is irreversible, and irreversibility is the arrow of time. Now I want to tell you about something called the block universe, because some physicists, actually, a lot of physicists think the past, present, and future all exist simultaneously. Like right now, your birth is happening somewhere in space-time, and your death is happening somewhere in space-time. And this moment, you watching this video, is also just sitting there frozen in the four-dimensional block of all events ever. In this view, time doesn't flow. There's no cosmic river carrying us from past to future. The universe just ice, all of it, at once. And what we experience as moving through time is more like moving through space, except instead of moving left or right or up or down, our consciousness is moving in the time direction. And the reason we move in our time direction toward higher entropy is because that's where the overwhelmingly large number of possible futures are. The block universe is mostly already determined by probability. The vast, vast majority of next moments are higher entropy moments. So consciousness, following probability, experiences time moving forward, even though forward is just a statistical preference, not a law. This stuff gets philosophers and physicists genuinely heated, by the way. Because if the block universe is real, if the future already exists, what does that mean for free will? What does it mean for causality? What does it mean for yo? We're not going to answer those questions today, but I love that they exist. I love that time. This thing you've been experiencing every single second of your life is still this deep, unresolved mystery. Let me give you one more brain-melting thought before we wrap up. There's a physicist named Sean Carroll who talks about this idea that memory is fundamentally a low-entropy phenomenon. Think about it. When you remember something from your past, your brain is storing a record of it. A physical, structural record. Certain neurons are connected in certain ways because of that experience. Information got encoded. That only happens in the direction of increasing entropy. Because encoding information requires an increase in order somewhere in your brain, which creates entropy somewhere else. You can only remember the past because the past was lower entropy. You can only anticipate the future because the future will be higher entropy. Your sense of time, the subjective feeling of it moving forward, is literally the universe's entropy gradient being experienced from the inside. You are the universe becoming aware of its own entropy. That's not poetry. That's physics. And here's the question that keeps me personally up at night. If we could somehow, impossibly, reverse all the entropy, if we could wind the cosmic clock back to the Big Bang and start again, would time feel like it's going backward to anyone inside that universe? Or would it just feel like time is going forward? Would the inhabitants of a low-entropy universe that's increasing in order experience that as their future? Some physicists say yes, that there could be pockets of the universe where entropy is locally decreasing. And in those pockets, beings would experience time running in what WE would call reverse. But from their perspective, it's just Tuesday. It's just the normal forward-moving Tuesday that entropy gives everyone. That's the universe. Indifferent to our sense of direction, just rolling downhill toward maximum mess. And we, tiny and temporary and wonderfully conscious, are along for the ride, calling the downhill direction forward, calling the uphill direction the past, drawing little arrows on our calendars and our physics textbooks, pretending we understand time, when really we're just inside it, counting arrangements, leaking information, becoming a little more entropic every single day. And that somehow is beautiful. The reason you can't go back isn't because of some cosmic law written in the stars. It's because there are just so many more ways to be tomorrow than to be yesterday. The universe isn't keeping you from going back in time. It's just that back is a door in a wall made of probability. And probability walls are the strongest walls in existence. Thanks for watching. And hey, the fact that you watched this far, that's already in the past now. Permanently, irreversibly, beautifully in the past. And there's literally nothing in the universe that can change that. Not even entropy.